So today we're talking about the quantum Fourier transform. Why do you want to do a quantum Fourier transform? Well, one reason is because it's a neat quantum transform, but that's not really the only reason. Another reason is it's a crucial ingredient in many of the quantum algorithms we found that speed up classical algorithms. And in fact, the fast Fourier transform was an ingredient in Simon's algorithm, although you didn't recognize it the way I presented it. So what is a quantum Fourier transform? Well, maybe I should say what is a discrete Fourier transform first. What is the discrete Fourier transform? Well, you have a sequence x0, x1, xn minus 1, and let's say n is equal to 2 to the L. You get a new sequence, y sub I equals summation. Okay, let's make it y sub j equals summation j equals 0 to n minus 1 e to the 2 pi I j k minus j over n, and this is taken mod n. So what we're going to do for quantum Fourier transform, and there's always a minus here on the forward Fourier transform and a plus here on the inverse Fourier transform. And that's more or less by convention. So for quantum Fourier transform, we're going to do roughly the same thing. It's a unitary. It takes the state k, 2, okay, it takes the state j to the sum e to the minus 2 pi I jk over n k j equals 0, 2, n minus 1, and we need a normalization constant. This, we're summing up n different kets with unit coefficients on them. So to make it a unit vector, we need to divide by 1 over n, root n. So this is the quantum Fourier transform. And in fact, it's the same as a discrete Fourier transform, except you really have kets, and here you have quantum states. Sum over k. Thank you. Okay. So first, is this unitary? Because I'm claiming it's a unitary. I'm claiming this is the unitary transformation. So what is the matrix for it like? Well, I guess k is over here, and j is over here, 0, 1, 2, 3 through n minus 1, 0, 1, 2, 3 through n minus 1. And eventually we will let n be a power of 2, but 2 to the L. But right now, we don't need to assume n is a power of 2. Well, the first row is e to the 2 pi I jk over n. J is 0. Oh, wait. I have got this backwards. I think. K, J. K is 0, so these are all 1. Then you get 1, e to the 2 pi I over n, e to the 4 pi I over n, and then 1 e to the minus 4 pi I over n, e to the minus 8 pi I over n, e to the minus 6 pi I over n, e to the minus 8 pi I over n, etc. So why is this unitary? Well, it's not the way I've written it. We need to divide the whole thing by 1 over root n because of this. So why is this unitary? Well, inner product of column B with column C is what? It's sum. We have two 1 over n root n's here, so they become 1 over n. And column C, the ith term in column C is e to the minus 2 pi I C. This had better be k equals 0 to n minus 1, 2 pi I C times k over n. And the nth term in column B is e to the minus 2 pi I b k over n. But because this is an inner product, we have to take the complex conjugate of this one. And this equals 1 over n e to the 2 pi I b minus c times k over n. And the first thing is if b equals c, this is e to the 0, which is 1. So equals 1 if b equals c, and 0 otherwise. And this would, so why is it 0 otherwise? Let's do it here. Well, if b is not equal to c, this is just 1 over n sum e to the 2 pi I. Let's call d k over n. b minus c equals d. And k equals 0 through n minus 1. So this is a geometric sum. And what we can realize is that 1 plus e to the 2 pi I d over n plus e to the 4 pi I d over n plus dot 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 times 1 minus e to the 2 pi I over d over n. So we're multiplying this by this. So this is a standard way of manipulating geometric sums. You should all have seen this before, but I'm just going over it again in case you've forgotten. You multiply this by this, plus that by that, and the first term product with this and the second term's product with this cancel, and the same here. This gives a minus e to the 4 pi I, and this is an e to the 4 pi I, etc. So you only get the first term and the last term, which is 1 minus e to the, well, the last term is n minus 1 times e to the 2 pi I d over n. So that's e to the n 2 pi I d over n, which is equal to 0 because d is an integer. So this is just e to the 2 pi I times an integer, which is 1. So this, everything cancels unless, so this says this times that equals 0. So either this equals 0 or this equals 0. This only equals 0 if d is a multiple of n. So otherwise, this term, which is the sum, equals 0. So we get this. So this matrix is indeed unitary, which means there is a quantum circuit that produces it. Of course, this does not mean that if n is very, very big, there's an efficient quantum circuit that produces it. So that's what this lecture is going to be on. How can you do this with an efficient quantum circuit?